Good afternoon, dear colleagues. My name is Nenad Petrovic. I'm a teaching assistant from Faculty of Electronic Engineering, University of Niš in Serbia at Department of Computer Science. I will present you the paper that we wrote together with my colleague George Kocic from Department of Electrical Power Engineering, who is a PhD student. Our paper is entitled Framework for Efficient Resource Planning in Pandemic Crisis. The topic is heavily inspired by recent global battle against COVID-19 pandemic. From many past scenarios, it's well known that pandemics in general have dramatic consequences. It doesn't only take human lives, but also ruins the economy, leading towards global crisis. However, many scientific works have shown that actually the protection of health and economy of a nation are tightly connected when it comes to pandemic crisis. In this paper, we present a novel framework whose goal is to provide efficient resource planning during the pandemic crisis. It makes use of several concepts and technologies, such as modeling, simulation, predictions based on deep learning, linear optimization, smart contracts, and blockchain technology. The presented case study is in context of current COVID-19 crisis. Now, let's take a look at the main facts about COVID-19 disease. During the first days of this year, in Wuhan, China, a novel flu-like disease was identified after several strange pneumonia cases. Behind this disease is SARS-CoV-2 virus, popularly known as coronavirus. After the outbreak in China, it quickly spread to other continents as well. However, due to its distinctive characteristics, this disease is much more dangerous than any flu-like disease in past. First, even the people without any symptoms might be potential sources of infection. Furthermore, it has quite long and varying incubation periods, making it almost impossible to handle the situation. To make the things worse, high death rate was shown among elderly and people with chronic diseases. Unfortunately, as for now, there is no approved specific treatment or vaccine for COVID-19. Due to all these facts, COVID-19 has taken a huge number of lives worldwide. Apart from that, it caused the stagnation of economy as well. Let's see some related work. It's already known that simulation approach can be very efficient when it comes to reduction of pandemic consequences. 14 years ago, simulation approach was used to tackle the past bird influenza pandemic. Just less than 2 months ago, the two scientists used the same approach to predict the spread of COVID-19 in Iran, which was one of the epicenters of the disease in the beginning. However, the work presented in this paper builds upon our previous work that has been approved for efficient energy trading in smart cities, leveraging the synergy of predictions based on deep learning, linear optimization, and transactions defined by smart contracts within the blockchain platform. The key concepts behind the proposed framework are deep learning, linear optimization, and blockchain technology. For deep learning, we relied on GPU-enabled TensorFlow library for Python. For linear optimization, we used Ample modeling language and Simplex solver, which is based on Simplex method. When it comes to blockchain, Ethereum platform was used as the backbone of transaction system, while Solidity language was used to define the smart contracts. On this slide, an overview of the proposed framework is given. In the first step, the user has to provide a CiiT resource model created within a web-based modeling environment. After that, the predictions about new COVID-19 cases and deaths are made using the deep learning approach, leveraging the data coming from publicly available online sources. In the next step, the linear optimization procedure is taken with respect to given models in order to reduce the resource exchange costs. Finally, the resource allocation matrix created as output of linear optimization procedure is taken as input of smart contract generation algorithm. The goal of this algorithm is to generate smart contracts between the involved parties and enable blockchain-based execution of transactions. The main aim of this framework is to reduce both the resource exchange and transaction costs in order to save as many lives as possible. For CiiT resource modeling, we introduce a custom domain-specific notation. On this slide, you can see a UML diagram defining the CiiT resource metamodel. The largest entity within the model is a map. Furthermore, each map contains several cities that are involved into resource exchange process. Several types of relevant resources are taken into account. First, the respiratory devices are needed in order to keep the critical patients alive. Moreover, the COVID-19 test kits are also crucial as they enable the identification of patients. It is known that the usage of masks and disinfection packs actually reduces the spread of COVID-19, so they're also considered. Furthermore, the human resources, especially the number of doctors available per city, is an important aspect. And finally, the number of hospital places available is one of critical factors when it comes to patient survival. On the other side, the weather parameters such as temperature, rain, and snow are also included as they affect the disease spread as well. For each map, it is possible to define a set of resource exchange strategies. A strategy consists of event such as lack of certain type of resources and response on the other side, which is a concrete optimization process used to tackle the situation. But when it comes to financial aspects, both resource and transportation costs on one side and CiiT budget on the other side are taken into consideration as well. The modeling tool is run in a web browser and doesn't require any additional installation. On the front end, JavaScript, CSS, and HTML were used for the implementation. On the other side, the backend was implemented relying on Node.js. This tool provides two distinct views: Map View, which shows all the involved cities, and City View, dealing with low-level details about resources for each of the cities. When it comes to simulation mechanisms, there are several conditions within CiiT resource model that are checked, as shown. In case that just one of them fails, the corresponding optimization strategy will be executed. With purpose of training the neural network, the daily online updates on global level and on city level in Serbia were used. CiiT identifier, the density of population, median age, the number of days within the year, temperature in Celsius, and moment hours during the lockdown were treated as independent variable, while on the other side the number of new cases and deaths were treated as the predicted values. We implemented several resource exchange optimization models, but only one of them related to test kit exchange will be described as example. The decision variable x has value greater than 0 in cases when resource exchange between the cities I and j will be done. In this case, it represents the number of test kits that will be exchanged. The objective function aims to minimize the sum of transportation cost and overall test kit price. However, there are two constraints. First, the number of test kits in each city after the resource exchange should not drop below the 10 times the number of new cases expected. On the other side, the overall amount spent in test kit exchange should not exceed the available CiiT budget. The ample code of the described linear optimization model is given on the right. In the last step, the resource trading matrix created as output of optimization process is leveraged to parameterize the smart contracts between the involved cities. The overall price is calculated and forwarded to smart contract as argument together with transaction source and destination address. The evaluation was performed on a laptop with given characteristics. The execution times for different steps and cost reduction with varying number of cities involved were recorded and compared. As it can be seen, these numbers depend on the concrete instance of the problem. The relative error of predictions was approximately around 30%, which explains the fact that the achieved results for cost reduction are slightly worse than in our previous work about similar framework for energy trading. According to the initial results, the proposed approach seems quite promising, providing the ability not only to reduce the necessary costs, but also enabling to timely allocate resources in a pandemic crisis situation and respond proactively. The proactive approach is of utmost importance as it can save many lives. However, the proposed framework is still a work in progress and needs much more data about new COVID-19 cases in order to have higher cost reductions and show better prediction accuracy. Thank you for your attention. This work has been supported by the Ministry of Education, Science and Technological Development of the Republic of Serbia.